Thank you everyone for coming to this talk. Today I'm going to talk about topology optimization of structural electrolyte microstructures using a topological sensitivity and level set approach. So before I begin, I'll just give a quick overview of what the talk's going to be about. So firstly, I'll give a very short introduction to my background before introducing the problem and looking at the full 3D topology optimization problem, and then a simplification that's been made to actually reduce that to a 2D shape optimization problem due to time constraints and difficulty. And then at the end, I'll go through a quick project overview and what's been done so far. So first of all, about me. So I graduated from the University of Sheffield in 2019 with an M.Math, and I'm now studying for an integrated PhD in advanced automotive propulsion systems at the University of Bath. I'm doing that as part of the Advanced Automotive Propulsion Systems Centre for Doctoral Training, and I'm currently the only math student, so I'll say a bit at the end of the presentation if there's time to try and encourage more people to come along. But that's enough about me for now. We'll go into the actual problem. So because of the CDT, I'm focusing on an automotive context. So I'm looking at structural batteries, but what is a structural battery? So it's a dual purpose battery focusing on being an energy storage device and also being a load bearing component. So for those not familiar with how a battery cell works, I'll give a quick overview. So using this image on the left here, we can see that we have a negative electrode, a positive electrode, and then a separator region in the middle called the electrolyte. And if the battery is discharging, so we start with all the lithium, focusing particularly on lithium-ion batteries, which are mostly found in vehicles. Our lithium atoms are all collected on the negative electrode, and then when the battery starts discharging, an electron separates from the lithium atom, passes through the vehicle circuitry to do whatever function is required, and the lithium ion, which is the lithium atom with an electron removed, diffuses through the electrolyte, and then the electron and the ion re-meet together again at the positive electrode. And then when you charge in the battery, the opposite happens. So the lithium ion diffuses to the negative side and the electron flows back through to the negative side. So that's how a cell works. And the image on the right here is how a structural battery might look in practice. So it's the same basic idea. We still have our negative connectors, which could be carbon fibers, for example. And we have a positive connector, and then this translucent material would be our electrolyte, and still the same thing happens. Lithium diffuses through the electrolyte between positive and negative. The advantages of structural batteries are that they can fulfill two functions in one component, so we can save mass and save volume, which is advantageous because by saving mass, you can increase the efficiency of the vehicle by reducing the amount it has to carry about and reducing the load on the engine and the battery and motors. But one of the problems with having two systems, two functions performed by one system, is that it's not quite as good at either as individual systems would be due to competing properties. And in particular, we're interested in looking at ionic conductivity and stiffness. So ionic conductivity is when the lithium ions are diffusing through the electrolyte, how much resistance is there to that motion? Conductivity is the inverse of resistance. So we want it to be highly conductive. And stiffness is how resistant the battery is to being compressed or squeezed or squashed, how well it holds up to those forces. So focusing particularly on the electrolyte, usually in batteries they're liquid because liquid has higher ionic conductivity. However, solid electrolytes are stiffer. And we can kind of reach a best of both worlds situation by using biphasic electrolytes. So this is where we have two phases. We have a solid phase, which takes care of the stiffness element, and we have a liquid phase which offers higher conductivities. And good results have been achieved by filling a solid porous mesh, so something like this on the left-hand side here, would be created first, and then filling that with a liquid electrolyte to fill up the holes. So what we've got here is the mesh on the left-hand side, and then an individual cell, which would be repeated in this mesh on the right-hand side. And just to note about the scale, we're working at the micrometer scale here, so less than the width of a human hair. So there'd be inside a battery cell, there would be hundreds, if not thousands of these. And a natural question to ask at this point, and kind of the point of this whole presentation is, given this mesh and these cells that make up the matrix, what is the optimal topology or shape of one of these cells to maximize both stiffness and ionic conductivity? And kind of the inspiration for this came from this paper cited at the bottom here. So the actual problem description, if we begin by denoting our matrix cell by sigma, which is a combination of sigma S, which is the solid phase, and sigma L, which is our liquid phase. We assume there's a known force applied evenly to the top and the bottom, and there's a given potential difference from one side to the other. And it doesn't really matter which side we say, because if it's discharging and charging, it's going to come from both directions. For now, for simplicity, we'll assume both of these are constant.
Sorry, Alex, can I interject? There is a question. Why is it not practical to just surround the battery with a very hard cell and use 100% liquid electrolyte inside?
If there's also other issues with having a liquid electrolyte, there are safety issues with having liquid electrolytes. At the minute, they do have a solid shell, but I can't say I've looked into it in that much detail, to be honest. For this presentation and for this work, I was focusing looking at optimizing these biphasic electrolytes.
Thank you.
Okay. But yeah, so the problem we're looking at is how can we maximize some cost functional that we define, which is going to be a linear combination of the ionic conductivity and the stiffness, where omega here is a parameter we can change. So when omega equals 1, we're focusing purely on maximizing conductivity, and when omega equals 0, we'll be focusing purely on maximizing stiffness, and anything between 0 and 1 would be some balance of that. And this cost functional is purely dependent on the solid phase, because if we affect the solid phase, then we're inherently changing the liquid phase as well, so we don't need to do it across the whole domain. How do we actually go about optimizing this then and changing the topology of it? So when we're looking at topology, we're looking at how the amount of holes and where the holes are in the region affect it. Or in our context, if we have the solid phase, we would, by inserting a hole, we're inserting a liquid region into a solid domain. And the topological derivative at a point in the solid domain describes how the cost functional would change if a puncture was made there. So if we insert a hole and introduce some liquid, how would that affect the stiffness and the conductivity? And then we can use this to inform a level set approach, which I'm not going to go into detail here, because it turns out I'm actually not doing the 3D problem to start with. Maybe that could be an extension afterwards, but for now I'm just looking at a 2D problem, which we'll get into in a minute. But we can use this in a level set approach and then to optimize the topology. So we would start by discretizing our initial domain in our level set approach. And then at each stage, it would be an iterative process. So at each stage, we evaluate our cost functional to see how this design holds up in terms of stiffness and conductivity. We then compute our topological derivative, which at this stage would just be putting numbers in and computing because we would already have derived it. And then using this, we can construct our new domain and then iterate those steps until the change in the cost functional falls below some acceptable tolerance. Now onto the 2D problem, because that 3D problem in the time frame I've got, which is about 6 weeks, which is now 4 weeks now, that was fairly intractable. So there is a 2D problem that's been simplified too. So now we're going to imagine looking at the same matrix. This is like a cross section of the matrix cell. So each of the squares above and below is like what part of one cell, and then this gap in the middle is where the liquid would flow through it. So we're looking at optimizing the boundary between the liquid and the solid phase. And the difference between shape optimization and topology optimization is here we're not interested in introducing new holes, we're just adjusting the boundary. And once again, just a reminder, we're working at the micro scale. So the shape derivative is defined as this. And once again, like the topological derivative, it tells us what is the change in cost functional going to be. But this time it's dependent on a velocity field V, which we would solve to find by saying, all right, we want an increase in the cost functional. We would solve to find an appropriate velocity field V. And then very much similar algorithm, apart from this time, we discretize our initial domain, evaluate the cost functional, and then we're computing the shape derivative instead of the topological derivative, and then computing the velocity field instead of our level set function and approach. And then we iterate that until it falls below the acceptable tolerance again, until we can say we've converged to an optimal shape. So now to get into a bit more of the details about the problem, what we can see here at the bottom is kind of an idea of what we might be working with. And we consider stiffness only in the solid phase and conductivity only in the liquid phase, because the solid phase is inherently stiffer than the liquid phase, and the liquid phase is inherently more conductive. So if we consider the stiffness in the liquid phase or the conductivity in the solid phase, this kind of amounts to a reparameterization and a different choice of our value omega. So for that reason, we can just consider stiffness in the solid phase and conductivity in the liquid phase. And our main boundary conditions for this are, we have a known force applied evenly along the top of the cell. And the reason that's not applied along the top and the bottom now is because we're assuming that the top and bottom halves are symmetric. So we only consider up until like the liquid gap. We also have zero displacement on the side walls, because if you imagine, we have lots of identical cells next to each other. So if one side wall pushes out, the one next to it is also going to push out and keep it balanced. Along the solid liquid interface, we assume that we have the equality of the liquid phase and solid phase stresses, which is also the same as having equality of the liquid phase and solid phase displacements. We assume that the lithium stays within the liquid phase and doesn't diffuse into the solid phase. So at the solid liquid interface, we also have zero lithium flux. And then finally, we have normalized lithium concentration and electric potential gradients across the cell. So we can say that because there will be a difference, if the battery is discharging, for example, say, at the negative electrode, there will be a high concentration of lithium to start with, and at the positive electrode, there'll be zero concentration. So we can say the same on the cell level. So we can say that at one side, we say the concentration is 1, at the other side, we say the concentration is 0, and the same for the electric potential. So what do we actually mean when we're saying stiffness here? How do we calculate this? Well, first of all, we model the solid phase as an isotropic elastic material. So isotropic here means that in any direction, the material is the same. So it's not like a wood grain where one side is more brittle than the other. And then we can describe the solid phase by the equations of linear elasticity. Here we have the displacement strain relation and the stress strain relation. So here we've got U is the displacement, tau sub S is the stress, which is the force per area of a unit. And epsilon sub S is the strain, which is the deformation or displacement due to the applied stress. And then capital C here is our stiffness tensor, which relates stress and strain. If we neglect body forces and assume that the solid phase has a uniform density of 1, then our equations of motion are given by this equation here, which is basically saying that the change in stress is equal to the acceleration. And then these are our governing equations for the solid phase. And we can find an expression for the stiffness. In optimization, a common way to express stiffness is to maximize stiffness is to minimize compliance, which is roughly the inverse of stiffness. And compliance is defined as the total strain energy. So strain energy at a point is given by this equation, so half times the stress tensor times the strain tensor. So if we want the compliance of the entire solid phase, we have to integrate over the entire domain. And then this gives us our instantaneous compliance of the solid phase. I'll touch on why it's instantaneous in a minute. Moving over to the ionic conductivity. So we're going to model the liquid phase, again as an isotropic material, but also incompressible viscous Newtonian fluid. And we're going to use the Nernst-Planck-Navier-Stokes system, which is a coupling of ionic diffusion and fluid motion. So these equations describe how the ions travel through the liquid, taking into consideration the motion of the fluid, the applied potential difference, and ionic concentration gradients. If we focus purely on lithium ions, which is what we're interested in, then we can have our ionic conductivity over the entire domain given by this equation here. So again, this is just integrated over the entire liquid domain, and what's inside the brackets is the ionic conductivity at a point. We've also expressed the fact that the liquid phase is equal to the entire domain minus the solid phase, so we can remove the need to include the liquid phase in our as a parameter for the cost functional. And what's important to notice about this is that the only variable in this equation is actually the concentration of lithium ions, because E here is our electric charge of the ions, D is a diffusivity constant, KB is the Boltzmann constant, and capital T is temperature. And in this equation, in this problem, we're assuming that it's isothermic, so temperature is constant. Initially, just to simplify it, this could change in the future to try and develop it a bit further. but for now we'll assume it's constant. Oops. So we're interested in how to find the concentration of a lithium ion. And that's modeled by the Nernst-Planck equation, which is a diffusion advection equation, where the concentration flux phi is given by this equation at the bottom. And this is where our fluid motion, the concentration gradient and the electric potential come in to affect the concentration. So here V is the velocity of the fluid at a point. We have the concentration gradient, and then we have this electric potential, which is given by psi. This potential defines an electric field, which satisfies this Poisson equation, which essentially says that in regions of higher charge density, the increase or decrease in the electric field, so the divergence of the electric field, is greater. So if we've got a region of zero charge, then there's no increase or decrease in the electric field. And then this also acts as a body force in the Navier-Stokes equation. So this is where the coupling comes in between these. So as well as the fluid influencing the concentration of the lithium ions, the electric field also has an influence on the motion of the fluid as well. So the acceleration here is dependent on the convection of the fluid, viscous diffusion, pressure gradient, and then this body force that's exerted by the electric field. So going back to putting this all together, our instantaneous cost functional is, if we recall, it was a linear combination of ionic conductivity and stiffness. We now have these terms here, and we can substitute these in to get our explicit expression for the cost functional. And the reason it's instantaneous is that so far there's no dependence on time in here. I almost put something in this week, but then I had to think about what do I actually mean by time in this situation, and that's something that I'm going to think about coming up, not in this presentation, afterwards. So that's most of what I've been doing so far, formulating the actual 2D problem, constructing the cost functional, and then the next steps will be to derive the actual shape derivative and create an explicit shape optimization algorithm, which can then be implemented numerically using code, for example, and then potentially extending the problem to 3D when I get to the PhD phase of the program, which I will say a few words about now. So the ABCDT is a fully funded 4-year integrated PhD program. So I'm actually not in the PhD program yet. I'm in the MRes phase doing my summer project. And the idea is that it kind of brings together students from a wide range of backgrounds to all work on similar problems and get different perspectives. So in my cohort, there's psychologists, chemists, engineers, me, a mathematician, and then a whole range of others as well. And it's a bit different to a traditional PhD because you get that cohort feel and you get that community built and you get to learn a lot of different skills. And the idea is that you become kind of a T-shaped researcher. So you have this broad range of knowledge that you can build from and like, but you also have your specific depth and you still have the PhD in your specific area. And it's very free to choose what this PhD topic is. So I chose an existing project, but you can also create your own. And I just really wanted to say something about this because I didn't know this existed until I came across it by chance on like findaphd.com. So I think it's important to like spread the word and say that there are other things out there. And on that note, I will finish there. Thank you for listening.